Welcome. Today, we're diving into GraphRAG, a cutting-edge approach developed by Microsoft Research that enhances retrieval-augmented generation using knowledge graphs. If you've ever felt lost in technical documentation or wondered how information is actually retrieved from a graph, this video is for you. We'll break down the entire process step by step, using a real-world example to make things crystal clear. By the end, you'll understand not just the theory, but also the practical workflow behind GraphRAG, including some search methods that aren't even covered in the official paper. Let's get started by setting the stage for what GraphRAG is and why it matters. GraphRAG stands for Graph-Based Retrieval-Augmented Generation. In simple terms, it's a method that leverages graph structures to enhance how information is retrieved and summarized in response to queries. Unlike traditional RAG systems that use flat document retrieval, GraphRAG organizes knowledge as interconnected entities and relationships, making it easier to surface relevant information. Microsoft's implementation breaks the process into two main steps: graph creation, or indexing, and querying. We'll focus on these steps, using the book Penitencia as our running example. Ready to see how it works in practice? To get started with GraphRAG, you first need to set up your project workspace. The documentation guides you through this process, and once initialized, you'll find a configuration file in your project directory. For our example, the book Penitencia is added to the input folder, and we use the default settings for indexing. This setup ensures that everything is ready for the next step, creating the graph. With the groundwork laid, let's move on to see how the graph is actually built from your source documents. Graph creation is the foundation of GraphRAG. This process involves extracting entities and relationships from your documents and organizing them into a structured graph. The workflow is automated. You simply run a command, and the system takes care of entity extraction and graph partitioning. These steps are handled by dedicated modules in the GraphRAG project. The result is a rich, interconnected knowledge graph that captures the key elements and their relationships within your data. Next, let's break down entity extraction in detail. Entity extraction is the first major step in building the graph. The source document is split into manageable chunks, each with a unique ID. Then, a lookup table is created to map these chunks to their parent documents. Using a large language model, entities and relationships are extracted from each chunk. For example, a character like John might be mentioned in many different chunks, so he appears multiple times in the raw extraction. These entities are then grouped and deduplicated, though some imperfections may remain. The goal is to capture all relevant entities and their relationships for the next steps. After extraction, the next step is deduplication. Entities are grouped by their title and type, while relationships are grouped by their source and target nodes. The language model is prompted to write a detailed description for each unique entity and relationship, synthesizing information from all occurrences. However, deduplication isn't perfect sometimes. Similar entities like John and John Marquez remain separate. Once deduplication is complete, the entities and relationships are represented as nodes and edges in a graph, using the NetworkX library, capturing the full structure of the knowledge graph. To better understand the structure, it's helpful to visualize the graph. Tools like Neo4j can be used to display entities as nodes and relationships as edges, making the connections clear. For instance, you can see how the character John is linked to others, or how relationships like that between Laura and Mario are represented. Visualization not only aids comprehension, but also highlights the complexity and richness of the extracted knowledge. This step bridges the gap between raw data and actionable insights, setting the stage for further analysis. The next step is partitioning the graph into communities using the Leiden algorithm. Communities are groups of nodes that are more closely related to each other than to the rest of the graph. This hierarchical clustering allows for communities of varying specificity, from broad root communities to highly specific subgroups. For example, in the book Penitencia, communities might represent different themes or character groups. Partitioning helps organize the graph and enables more targeted querying later on. Visualizing communities reveals clusters within the graph. Each community can be seen as a node with its own set of entities and relationships. For example, you might see a root community with several subcommunities, each focusing on a specific theme or set of events. This visualization helps identify overarching topics and how different parts of the document are interconnected. It's a powerful way to gain big-picture insights from complex data. After partitioning, the system maps entities, relationships, and covariates to each text unit. Covariates are essentially claims or inferred statements, like Celia murdered her husband and child. Suspected. This mapping makes it easier to look up all relevant information for any given chunk of text. The process ensures that every piece of extracted knowledge is linked back to its source, supporting traceability and detailed analysis in later steps. For each community, the language model generates a detailed report, summarizing main events, themes, and key insights. If the context for a community is too large, the system uses hierarchical substitution, replacing raw data with sub-community reports to reduce length. If needed, further trimming removes less relevant entities and relationships. The final report combines a summary and a list of insights, providing a comprehensive overview of each community's significance within the document. The final step in graph creation is generating embeddings for all text units, entity descriptions, and community reports. These embeddings are vector representations that allow for efficient semantic searching. When a user submits a query, the system can quickly find the most relevant parts of the graph by comparing embeddings. This step is crucial for enabling the powerful search capabilities that set GraphRAG apart from traditional retrieval systems. Graph built, you can now query it. Local search is used for specific questions. The system loads all relevant data, embeds the user query, and calculates its similarity to each entity. The most similar entities are retrieved, and their associated communities, relationships, and text units become candidates for answering the query. These candidates are sorted and prioritized based on relevance and importance, ensuring the most useful information is included in the context for the language model to generate a detailed response. During local search, candidate communities, entities, relationships, and text units are selected based on their connection to the extracted entities. Each type of candidate is sorted differently: communities by matches and rank, entities by semantic similarity, relationships by network type and degree, and text units by entity order and relationship count. This careful prioritization ensures that the language model receives the most relevant context, maximizing the quality of the generated answer. Once candidates are prioritized, their descriptions are concatenated and provided as context to the language model. The model then generates a detailed response to the user's query, drawing on the most relevant community reports, entities, relationships, and text units. This process ensures that answers are both comprehensive and contextually grounded, leveraging the full power of the knowledge graph. Now, let's see how global search works for broader questions. Global search is designed for general questions about the entire document or dataset. The system loads all community reports and entities, calculates an occurrence weight for each community, and shuffles them to reduce bias. Communities are then batched and sorted by their weight, ensuring that the most prevalent topics are prioritized. For each batch, the language model generates multiple responses, which are scored and ranked. The best responses are then combined to form a final, comprehensive answer to the user's question. After generating and scoring responses for each batch in global search, the texts of the top responses are concatenated and passed to the language model one last time. This final step produces a unified, well-structured answer to the user's general question, drawing on insights from across the entire graph. The result is a summary that reflects the most important themes and findings, providing a holistic view of the document or dataset. We've walked through the entire GraphRAG workflow, from graph creation to both local and global querying. This approach not only organizes information in a highly structured way, but also enables powerful, context-aware search and summarization. As you explore GraphRAG further, consider experimenting with different configurations, fine-tuning prompts, or trying alternative indexing methods. The flexibility and depth of GraphRAG make it a valuable tool for anyone working with complex, interconnected data. Thanks for watching, and happy experimenting.